Good day, my dear students. Sorry for the late upload of this lecture, as we were advised by the administration that during the academic relief and the succeeding 2-week suspension of classes, we are not to upload any reading materials for students, and we do not require any submission coming from you. And since it's just 2 days prior to the November 30 end of the no classes period, here I am. Okay, the design of the STP that I've required of you is just based on the premise that you have to service a business center located in Santa Ana. Okay, so just a brief background, the STP that I'm requiring of you should just contain a primary treatment and a secondary treatment. So ito lang yung nire-require ko. Since for the WWTP, the only time that you require a tertiary treatment is that if your effluent is due for recycling or to be used in any other process other than just disposing it in any body of water. So for the design that I required of you, all the effluents just be discharged in the nearest river or any body of water. Okay, so ang kailangan ko lang is that for you to design the plant capacity, the design of the screen, the grit chamber, the sedimentation, aeration, the secondary sedimentation tank, and partly siguro konti lang about your disinfection and your sludge drying bed. Okay, so basically it's like this. So you are to service, assuming these are the buildings in the site development. So we need to determine first the plant capacity. So how much sewage are we going to generate per day? So first is you have to do an assumption of the average water supply per day. So once you know the average water supply per day, you can compute for the average sewage generated per day. Okay. And this is mostly 85% of your average water supply. So once you know that, you just need to have an assumption of the peak factor for you to know the design flow capacity. Because from here, design flow capacity, it will be your basis in sizing your receiving tank, your grit chamber, the primary, up to the sludge drying bed. So design flow capacity is just the average sewage generated multiplied by the peak factor. Okay? So yan yung magiging capacity mo. Okay. So let's go to the sizing of the receiving tank. From here, you have to have an assumption of your retention time, how much time you would want your sewage to be staying in your receiving tank. Because from that, you will get to know the capacity of your collection, of your receiving tank or collection. Sometimes it's actually termed as collection sump. So from here, assuming, lagay ka, say, 3 or 4 hours, your capacity of the collection sump is, this actually is your volume of your receiving tank. Okay? It's just the average sewage generated or the average design flow, yung kaninang kinompute natin, multiplied by, so it's actually flow times retention time. Do note that the average sewage generated per day would either be in million liters, megaliters per day, or in cubic meters. So kung ang flow na na-compute mo kanina is in terms of cubic meter per hour, times your retention time in hours, so you get it, the volume of your receiving tank. Once you know the volume of the receiving tank, you get to have another assumption. This is your liquid depth. And usually, Ito siguro hindi naman pwedeng mag 10 meters, so masyadong malalim. So, assuming you have a 5 meter liquid depth, you can get the area. It's because area of the receiving tank would just be the volume over the depth. Okay? So, you'd get it in meters squared. And then, based on design premises, the length to the breadth ratio is always 2:1. So just show L times B, we just have a ratio of 2:1. Knowing your area, diba? Area is just length times the breadth. So L times B. Alam mo to, you know the ratio of L over B, or L times B is 2:1. You could now compute for your breadth and your L. Once you know this, the size of your receiving chamber would then be L times B times the assumed liquid depth. So times the depth. And usually, there's a design factor of 0.5. 0.5 here. Now, how are you going to check if your assumption for the depth is correct? You should compute for the volume design. Yan actually si L times B. This should be greater than or equal to the volume required. Where is the volume required? Yung volume na na-compute mo dito. Okay? Once you satisfy this equation, then you're good at the design of your receiving tank. Okay? Let's go to screen. For the sizing calculation of core screen, whether it's manual or mechanical bar screen, the maximum velocity, the Vmax of dish, should never exceed 0.9 meters per second. Why? This is to prevent washout of solids through the bar. So kung masyadong malakas yung velocity, pwedeng makapasok yung other solids. Okay? Okay, how are you going to design now your core screen? From your peak discharge, or the average sewage generated per day, so the peak discharge, sabi ko kanina, if your assumption from the very start that your average water supply is assuming it's 10 megaliters per day, the average sewage generated is 85% of the 10 MLD. That is around 8.5 MLD. Convert MLD into cubic meter, or the megaliters per day, convert that to cubic meter per hour, or the peak discharge could either be also in cubic meter per second. And assume again a maximum velocity. Take note, any velocity should should not be greater than 0.9. So assuming ako ng maximum velocity, which is a 0.6 meters per second, I could compute for the AC. What is the AC? It's a channel cross section. This is the channel cross section. The channel cross section is basically the peak discharge in cubic meter per second divided by the maximum velocity in meters per second. So you get that in meter squared. Now, knowing your cross-sectional area, and usually all core screen are designed to be rectangular channels. Wala man siguro maglalagay ng circular, right? Now, for rectangular channels, the depth to width ratio naman nito, and width ratio is always 1.5, or D over W. So depth over width is equivalent to 1.5. Since you know your cross-sectional area, AC, and this is D times W, knowing that 1.5 is equal to D over W, you could compute for the value of your depth and the value of your width. So once you know the value of depth and your width, You now compute for the cross-section area of the screen. So this is actually the AC is the channel cross-section. You also have your AS, which is the area of the bar screen. So this is the cross-section of the bar screen. Later you will learn the relationship between the AC and the AS. So usually AS is given by the formula that your cross-sectional area, AC, divided by sine of theta. Theta is the theta of inclination where screen bars are being placed to the horizontal. So usually ito is, the theta is taken from 45 degrees to 70 degrees. But commonly, theta is assumed to be 60 degrees. So once you know AC, so this would be your AS, the AC here, divided by sine 60 degrees. Okay? Now, knowing AC and AS, the net area, therefore, of the bar screen would then be, from the formula, area net is equal to AS, this is the cross-section of the bar screen, times S over S plus the thickness of the bar. What is S? It is the space between the bars. So that is your S. And usually, this ranges into centimeter lang. Wala naman siguro maglalagay that the area between your bars would be 1 meter. It's too wide that some solids would pass through. So assuming that your S is, assumption lang, S is chosen to be 3 centimeters. Tapos yung T-bar ko, assuming it's 1 centimeter, you'll get therefore your net area to be equivalent to AS times 3/4. Or 3/4 of the AS is your net area. Okay? For me to be able to check that all my assumptions from the maximum velocity up to the theta is correct, from my continuous equation that VA times the cross-sectional area should be equivalent to the VB times net area. You know that the VA is the maximum velocity. So you have this one. So your VB therefore is the VA, the maximum velocity, the 0.6 there a while back, times the cross-sectional area divided by the net area. If your answer is less than 0.9, you're good then of your assumptions. Okay. Once you know this one, you know already the cross-sectional area of the screen. You can now compute for the number of bars. You know the cross-sectional area, you know the thickness of each of the bars. You're now ready to check on or to compute for the number of bars needed. So the number of bars N is equivalent to N times the thickness of the bar plus N minus 1 times the S, which is also equivalent to the width or your W. Kanina, ang nakuha natin around for the W is around, diba, inassume natin na it's just what do you call that? Yung makukuha mo dito sa DW from your computation. So whatever is the value of this, substitute it here. You know that N, so your N times the thickness of the bar, which is 1.0 centimeter. Ito yun, the thickness of the bar, 1.0 plus N minus 1 times 3 centimeters S, 3.0, is equal to the W that you got here. Then you can compute now for the value of your N, which is the number of bars that you'd put it covering the net area that you got. Okay? Now, next, we proceed with the grit chamber. So, sizing or calculation of grit chamber, you again go back to your peak discharge or the sewage generated. So, the peak discharge, so mag-start na naman tayo, peak discharge of sewage. You got it in, say, cubic meter per second. You now assume another detention time, the detention time of your wastewater inside your grit chamber. So, say your detention time, your assumed detention time is 3 minutes or 3. So, kung 3 minutes, that's actually 180 seconds. So, kung ito is 180 seconds, you could get for the aerated volume. It's a volume which is your peak discharge times the detention time. So, ito na naman ulit, si aerated volume of your grit chamber, which is your peak discharge, sorry for that, times your detention time, which is cubic meter per second times 180 seconds. You get that in cubic meter. Okay? Now, for routine cleaning, usually your chambers would you would need 2 chambers. Para pag nililinis mo yung kabila, umaandar yung kabila. So, whatever is the volume here, you divide it by 2. So, that would be volume of each chamber. So, volume of each chamber would then be the total volume divided by 2. Okay? Now, you have to assume the depth, which is the width to depth ratio again would be 2:1. So, the width ratio, the depth to width ratio is 2:1. 2:1 again. So, kung i-assume ko na 1 meter yung depth ko, my width would be 2 meters. And the length of the channel. So, kung ang width ko ay 2 meters, 1 meter to ang length ng buong channel, therefore, would be the area of each chamber, the volume actually, the volume of each chamber, ito, so that the volume of each chamber divided by, to get the length, divided by the width and the depth. So you get the length. So you'd have now the length times width times depth of your grit chamber. Okay? We proceed with, again, with your primary sedimentation tank. So usually, ginagamit is a circular tank which makes settling by allowing a radial flow, diba, sa primary sedimentation tank. So you get, again, go back to your maximum quantity of your sewage or the peak discharge in MLD. So again, if you assume that it's 10 million megaliters per day times 85%, so you get this as 8.5 MLD. This is just for calculation process lang. So your surface loading or overflow rate, i-assume mo siya, halimbawa 60 cubic meter per square meter per day. Mag-a-assume ka na naman ng detention time. So once assuming a detention period mo is 1 hour, you get the volume of your sewage to be, again, your peak discharge times detention time. The peak discharge in, say, this in cubic meter per hour times detention time in hours. So you get that in cubic meters. Now provide for the effective depth. This provision is assuming it's 2.5. So kung alam mo yung depth, you'll get to know your surface area of the tank, which is basically your total flow. So kung meron ka ng depth, ang surface area naman ng tank would be your total flow divided by surface loading. Itong surface loading, sabi ko kanina, it could either be your kanina it was just 8.5 mld, so that's around halos 8,500 divided by kung 1 hour ang detention period ko. Surface loading, you have a 60. And that the area of the surface tank is, of course, circular, pi over 4 d squared. Once you know area, you could now get for the diameter of the tank. Okay? So, makukuha mo si diameter ng tank. Or, if you want, another way to get this one is using the volume. Once you know volume, di ba? You know the volume of a tank is equal to pi over 4 d squared times the height. Meron ka ng effective depth na 2.5. You know the volume. So, alam mo si volume, you know effective height. You could check for the diameter. Either of the two, whether it's a total flow or the surface loading, you'll get the same value of your D. Therefore, you'd get that the primary sedimentation tank dimension, the dimension of the tank finally, therefore, is equivalent to the diameter that you have computed here times the depth of 2.5. And this is always plus 0.5 factor. Correction factor. Okay? Okay, knowing that one, we now proceed to, so ito usually circular, yung primary sedimentation tank. I think this figure was included in the previous lecture that I have uploaded before about wastewater treatment. Okay. We go to the aeration tank. Ito yun. For the aeration tank, usually dalawang ginagamit. So, kung dalawa din yung kanina dun sa grid chamber. So, if you're using the number of aeration tank to be 2, the design flow is again the 8.5 megaliters per day, the peak discharge. So, kung ang design flow ko ay pegged to 10 megaliters times 85%, so that 8.5 megaliters per day, the average flow for each tank would be, the average flow for each tank would just be the 8.5 mld divided by 2. Or if you're to compute 8.5 mld to cubic meter, that's times 1,000. So you get 8.5 times 1,000. So divided by 2 tanks. So flow for each tank is around 4,250. So ito halos 4,250 cubic meter per tank. So, take note that this is for computation purposes. Depende kung ano in-assume mo na design flow mo from the start. Okay. Assuming that your BOD at the inlet is 300. Yun ang BOD mo from the inlet. And, therefore, your BOD dito sa inlet ng aeration tank mo would just be 0.8 or 80% of the 300. Why 80%? It's because the 20% of the BOD, so usually 20% of the inlet BOD, 20% of inlet BOD is already removed in the grid chamber. So 20% of inlet BOD is already removed in the grit chamber. So, ang matitirang i-remove mo dito sa aeration tank would just be the remaining 80%. Okay? So, this is already removed in grit chamber. So, kung kanina 300, assuming you have a 300 BOD, what's the value of your BOD to be treated here in your aeration tank would just around be 240.8 times 300. Okay? Therefore, ang BOD ko na lang at outlet is 20 ppm. So, you would have the maximum efficiency, therefore, of your aeration tank would be 220. Kasi kung ang outlet mo, you assume na 300 BOD at inlet. Tapos kung ang outlet mo, BOD at outlet, ito yung target mo, is around 20 ppm na lang, supposedly, your maximum efficiency is 240 minus 20, you get 220, all over 240, which is times 100. So, maximum efficiency mo is, 220, 240. So, that's around 91.67 or 91.7% efficient. Okay? So, ang MLSS mo is 300, is 3,000 ppm mixed liquor, and your F over M ratio is equivalent to 0.4, knowing that F over M is equal to Q times BOD all over the V times MLSS. You'd get the volume of the tank, of your aeration tank, to be equivalent to F over M by F over M times MLSS divided by Q times BOD. So you get the value of your V. Knowing the value of your V, you again assume a depth, the depth of the tank, halimbawa 5 meters or 4.5 meters. Alam mo si volume, and then the width to depth ratio is equivalent to 2.2. You'll get the value of the width, and then computing for your length. So kung alam mo si depth, which is 4.5, tapos width to depth is 2.2. So kung 4.5 to, your width would be 4.5 times 2.2, so around 10. So knowing your width and the depth, you could compute for your length, which is basically the volume here divided by the depth times the width. So that's your length. Now, for us to check for the aeration period or hydraulic retention time, your hydraulic retention time, HRT, is actually V over Q times 24 hours. So kung per day, so times 24 hours. And HRT should always be in between, the value should be 3 to 6 hours only. Okay, so it's the volume here that you got, itong volume na to, divided by your Q, which is the average flow for each tank. Ito yun. So, this V divided by 4,250 cubic meter, assuming nag-start tayo nga na 10,000 MLD. So, the HRT, your hydraulic retention time, must be between this range. So, if it is within this range, your dimension, therefore, is this times the depth times the length. So, ang dimension mo of your aeration tank would be length times the width times the depth. Okay? Now we go secondary sedimentation tank. Again, we'd always start with the average flow. kanina, so this is for the nth time. If I assume that my average sewage is average water supply is 10 mld, 85%. So you have the average flow. It's the average flow of 8,500 kasi 8.5 mld times 1,000 liters per cubic meter. So you get 8,500 cubic meter per day. The recirculated flow would always be assumed 53% ang recirculated. So this would all depend on your assumptions, okay? So if my recirculated flow assumption is 53%, so I get 0.53 of my 8,500. So you get that in cubic meter per day, recirculated flow. Therefore, your total inflow is the average flow plus the recirculated. So the average flow of 8,500 plus your recirculated flow. And then, HRT, your hydraulic retention time, assumption na naman. Assume your HRT in your sedimentation tank. So kung halimbawa, nag-assume ka, ang HRT ko is 2 hours. You then get the value of your, the volume of your tank to be the total inflow times 2, 2 hours. So that the volume that I'll get for my secondary sedimentation tank is the total inflow. Ito yung total inflow, which is your recirculated plus your average flow. So it's total inflow times your HRT times there are 24. So since HRT is in hours, total inflow is in cubic meter per day divided by 24 hours. Okay? So you get that in cubic meter. Again, depth. So laging depth ang ina-assume natin. Assume depth of the tank. Sige, let's say 3.5 meters. So if I have an assumption of 3.5 meters, then the area that I need is the volume divided by the depth of the tank. Okay? And if your surface loading rate of average flow would be, siyempre, assume ka, bawa, 25 cubic meter per meter squared per day, the provided area, surface area provided, therefore, would be yung total inflow, the average, is average flow, kung surface average flow is 25, so 85 divided by 25. And whichever is the larger, you use that area. Kasi diba, you have the area that you'll get here. You could also have, sabi ko, an area based on the surface loading rate. Surface loading rate at average flow, of average flow. Kung halimbawa nag-assume ako dito na 25 cubic meter per meter squared per day, makakakuha ako ng area to be, or the area provided would be the average flow divided by the average loading rate. So that is the 8,500 divided by 25. So any value of this, whichever is greater, this A1 or A2, so whichever is greater between the two, you use that area. Kung mas malaki itong mako-compute mo dito, you use A2. Okay? If A1 ang mas malaki kaysa sa A2, you use A1. So that would be your basis in getting the diameter of the tank. Once you know area, again, since it's circular, it's just equivalent to pi over 4 d squared. So you know the area, you can compute for your d. Now, you have to check for your wear loading. Its average flow area, 8,500 cubic meter divided by the length. So, flow rate times length of the wear or yung diameter. Okay? So, if I'm to check for the wear loading, it's basically the average flow. So, makukuha ko dapat na wear loading is the average flow, which is this, divided by the diameter times pi. Okay, so do you get that? So, yung makuha mong value dito na D times pi. So, that would be in cubic meter per day per meter. Okay, so because this is cubic meter per day. Cubic meter per day per meter. Okay, so ang wear loading mo is cubic meter per day. Now, let's check for the solids loading. Check for solids loading. For you to be able to check the solids loading, you get to have the recirculated. Ano yung recirculated flow ko? Ito. And then your MLSS to be kanina, we pegged that I think to 3,000 ppm or milligram per liter. So, yung recirculated flow plus yung MLSS, kung 3,000 kanina na ipeg natin, 3,000 milligram per liter, so that's 3 kilogram per cubic meter. The total solids flow would be the average flow plus the recirculated, which is the total inflow. Total inflow times the MLSS. So, yung solids flow, total solids flow is equivalent to your total inflow times your MLSS. Okay? And that is given in kilogram per day. Once you know your total solids flow, you get your SLR or solids loading rate, which is the total solids flow divided by the surface area. So, whichever is the greater between the two. So, surface area. So, you get that in, kung ang total solids flow ko is kilogram per day, ito yun, divided by the surface area in cubic meter, meter squared. So, you get your SLR or solids loading rate to be in kilogram per day per meter squared. Now, the range should either be from 100 to 150. So, ito lang yung value. Should be in between 100 to 150. Okay, so that's kilogram per day per meter squared. Now, once you know that one, kung na-check to, pasok yung computation for SLR, therefore, the dimension of your sedimentation tank would just be the diameter that you get here. So, ito yung dimension na therefore would be the diameter that you have computed times the depth na inassume mo. Otherwise, if you exceed this one, if you're not within those range, your assumption for depth is wrong. Okay? Okay, finally, for your sludge drying bed. So, from our previous lecture, these sludge drying beds are open beds of land. Could either be from 45 to 60 centimeters deep and 30 to 45 centimeters thick, graded layers of either a gravel or crushed stone, varying in size from yung stones would either be from 15 centimeters at bottom and 1.25 centimeters at the top. So, parang mas pino nasa ibabaw niya. So, either it's in open jointed under drain pipes. So, meron ka diba sludge drying bed. So, pwedeng meron kang mga pipes dun sa baba. Okay? And this would be, usually kapag large beds, These are portioned by concrete walls. My pipe header and digesters were gated with openings to allow application of sludge independently to each cell. Okay, so we go back to the design. So your sludge applied to drying bed, a-assume ka ngayon ng amount of sludge that you are putting in your drying bed. So, halimbawa, assume ko 100 kilogram per megaliters per day. Ang assume ko. The sludge applied is, again, the 85, right? 85 mld or 850 kilogram per day. Ang solid content, assuming natin dito is around 2%. Specific gravity of more than 1. So, halimbawa 1.015. So, you could get now the volume of the sludge. You have the solid content of, the total sludge applied per day. So, that the volume of your sludge would be your 850, the total load, kilogram per day, times the 2%, times 850 kilograms of in cubic meters, I would have 1,000 times your 1.015, which is a specific gravity. So you get that in cubic meter per day. The number of cycles in 1 year, assuming it's 365 days per 10 days. So, 10 days ang 1 cycle ko. So, if number of cycles in a year, you have 365. Assuming per cycle ko I have 10 days. So, roughly 37 cycles. So, 37 cycles, which is, per cycle is, so, ang 1 cycle is equivalent to 10 days. Okay? So, the volume of sludge per cycle, therefore, is eto times the 10 days. And then, if you are to spread it 0.3, so the volume of sludge per cycle would be this times the 10 days. And then, if you are to spread it, assuming 0.3 meters per cycle, ang makukuha mo na area of the bed is equivalent to the volume of sludge per cycle divided by volume of sludge per cycle divided by your 0.3 meters per cycle. Okay? So, you get that in diba, cubic meter yung volume. So, this is cubic meter ang volume per cycle divided by 0.3 meters. So, you get that in meter squared, area of the bed. Now, if 5 beds are provided, you divide this area divided by 5. So, ang area ngayon ng each bed mo, assuming, sige, just for computation purposes. So, we started at 850. Let's compute for that. 850 divided by 0.02 times 1,000. Wait. 850 divided by 0.02 times 1,000 times 1.015. 15. So, you get the value to be 41.9. So, kung 41.9 to, for computation purposes, kung 41.9 yan, you get the volume of the sludge to be 41.9 times 10. Kasi may 10-day cycle ko. So, ang volume of sludge per cycle is 41.9 times 10. So, you get 419. So, the 419 divided by 0.3 you get a value of 419 divided by 0.3. You get a value of 1397. So, kung ang area ko is 1397 meters squared, assuming that I am provided, ang provision natin is 5 beds, area of each bed therefore would be 1397 divided by 5. So that's roughly 280. So it's 1397 divided by 5. You get around 280 meters squared. So if the area of each bed is 280 meters squared, it's now for you to get the rough estimate of length times the width. So 280, it can either be 20 meters times 14 meters na bed. So it would be up to you kung ano ang pinaka best na area, best na dimension having an area of 280 meters. Okay? So basically, that's all that I am asking of you. This is just a simple STP. And note that all computations definitely will adjust when actual volume of water supplied is available. Halimbawa, ang assumption natin would be per capita basis. Kung ang per capita basis natin is 235 liters per capita per day, so dyan manggagaling yung computation mo from the start, which is your assumption of the average water supply. And then, assuming still the number of sewage is 85% of that, and all computations will roll based on this available water. Okay, so that's all. And thank you. I just hope you were able to follow a simple computation. Sabi ko nga, it would just be the same, very simple STP that I'm requiring of you. Just compute for the plant capacity, dimension of receiving tank, the screening, grid chamber, and lastly, yung sludge drying bed. Okay? Thank you and have a great day.